Hello, welcome to Cosmology Talks. Today we have Johannes Lange, who is a postdoc at the University of Michigan at the Lineweaver Center for Theoretical Physics. Today he's talking about lensing and clustering at the nonlinear scales. In particular, he's combining the kilodegree survey, the dark energy survey, and BOSS, the Baryon Oscillation Spectroscopic Survey in various ways. This is interesting because I believe this is one of the most ambitious attempts to include these nonlinear scales, especially perhaps with respect to Redshift-Space clustering, as we'll see. Whether we think we're ready or not for these nonlinear scales, and whether we think Johannes and his collaborators have made the right cuts in modeling decisions, it's interesting to see what an analysis about these scales actually says, especially as we have this S8 tension and systematic errors from data on the nonlinear scales and modeling at the small scales should be at least slightly different from the larger scales. And we do see that the S8 tension survives on these nonlinear scales, though in this particular analysis only at the 2 or so sigma level, which is, I guess, common in most analyses. The thing that's interesting about the S8 tension is, of course, always that it's just present in all of the large-scale structure analyses. One would imagine the combined tension must be much, much larger, even though it's a very difficult analysis to do. But enough from me. Welcome, Johannes. Do you want to start by telling us briefly about your paper?
So we present a cosmological analysis of galaxy redshift-space clustering in BOSS-LOWZ, as well as galaxy-galaxy lensing, cross-correlating BOSS-LOWZ with the lensing catalogs from the kilodegree survey and the dark energy survey. And the focus of this work really is to push the analysis down to highly nonlinear scales. And I think this paper really highlights a lot of the advancements that have been realized in the past few years in modeling highly nonlinear scales and really analyzing the full range of scales that we can measure with state-of-the-art data. And so in this work, we, for example, perform extensive tests and verification on mock catalogs to ensure that our cosmological constraints are unbiased. We also marginalize over various astrophysical effects, like, for example, velocity bias or galaxy assembly bias. And our actual analysis on the data is performed blindly with respect to cosmology. Ultimately, we obtain two complementary, somewhat independent constraints on S8. One comes from analyzing just galaxy redshift-space clustering, where the constraints on S8 come from basically redshift-space distortions. And another constraint on S8 comes from the combination of projected clustering and galaxy-galaxy lensing. So we filter out the redshift-space distortions, and the constraints come only from lensing. And so both these constraints are very stringent and consistent with each other, and they both are around 2 sigma below the CMB value and add additional evidence for the existence, the possibility of an S8 tension.
Is it true that you've kind of gone to more nonlinear scales than analyses of at least DES and KiDS? I guess HSC have maybe gone to similar nonlinear scales, but
if you want to directly compare it, yeah, so you on this channel you had a recent talk by the KiDS collaboration. They went to similar scales, so also going down all the way to the 1 halo regime. HSC has done a similar analysis of projected clustering and galaxy-galaxy lensing. I would say they don't go down to quite as small scales, but similar. I would have to look it up. I'm actually not 100% sure. I don't think a similar analysis exists for DES. The DES analysis, they're more conservative in the scale cuts.
So if people are remembering this talk 6 months from now and your paper 6 months from now, and there was nothing else they remembered except 2 things, what would you want those 2 things to be?
Yeah, so I think there are 2 important points, both related to analyzing nonlinear scales. The first thing is the constraining power that we can obtain by pushing the analysis down to nonlinear scales. We show that for the same data set, by extending the analysis to these small scales, we get a factor of 2 or 3 better constraints on cosmology, particularly S8, and that's even after marginalizing over various astrophysical effects, like I said, galaxy assembly bias or velocity bias. The second point is related to the robustness of these results. There have been several advancements in the modeling of nonlinear scales. Most of these analyses are now based on simulation-based modeling, so we directly compare the predictions of simulations against observations. As I said, we do this analysis blindly. We verify it on mock catalog. We had results that are very stringent and still very consistent with other large-scale structured probes. And so it really shows that there's quite some reason to believe that these results are robust.
Right, and the consistency, I mean, I guess you've still got the same large scales as the other analyses, but you're error bars have shrunk because of the new small scales. So if the small scale modeling was inconsistent, you would expect, I guess, some sort of shifting rather than staying at the same. So yeah, like why did you do this? I guess every time we talk about S8 or H0 tensions nowadays, it's that part kind of doesn't need motivated anymore. But feel free to give your own perspective on that. But perhaps also nonlinear scales is self-evident that it's where more information is. So feel free to give your own thoughts on that. But beyond that, yeah, why your particular methods of simulations and things like that? What's and also why is this coming out in 2023 and not 2025 or 2020?
Yeah, so one of the motivations for this work, and I don't think I need to talk about this because it has been mentioned quite a few times on this channel, is the possibility of the existence of an S8 tension. So when we analyze large-scale structure statistics at low redshift, we tend to infer a lower value for S8 than what we infer if we look at the CMB, particularly Planck, and assume lambda CDM. And typically, the discrepancy is at the order of 2 to 3 sigma, and so no individual study by itself can yet claim this 5 sigma threshold, but this motivates trying to get more cosmological information out of the same data. And one way to do this is to analyze or to push analysis down to nonlinear scales. So typically, when we analyze the clustering of galaxies and matter, we would concentrate on the distribution on fairly large scales, scales of tens of megaparsec or larger. On those scales, the matter distribution can be very accurately predicted from perturbation theory, and also the relationship between the galaxies that we observe and the underlying matter field is fairly straightforward. If we want to push analysis down to smaller scales, we're encountering additional complications. So the density contrast will increase, and eventually you encounter gravitational nonlinearities, which means perturbative approaches will break down, and we have to run expensive n-body simulation of cosmic structure formation. Additionally, if we go down to scales of 10 megaparsec or smaller, we also have to worry about what exactly is the relationship between the galaxies we observe and the underlying matter field. A more precise relationship between the galaxies and the dark matter halos that hosts them, which is known as the galaxy-halo connection. And finally, if we're interested in analyzing the matter distribution on scales of a few megaparsec and smaller, we also have to worry about baryonic physics. So for example, AGNs will launch outflows from the centers of dark matter halos, which will evidently affect the matter distribution on those small scales. So as you can see, if we want to push analysis down to smaller scales and analyze the full range of scales that we can get measurements for with current data, there are these additional challenges we need to overcome. At the same time, a lot of recent work has shown that if we're able to do so, we can also expect to get much more stringent constraints in cosmology, particularly on this S8 parameter. So that's the main motivation for the present work. And all this kind of analysis really has been made possible through several advancements in recent years. One is the step towards simulation-based full-forward modeling. So typically, in these types of analysis, you would take some large dark matter simulation and then populate them with mock galaxies according to some recipe, and that recipe is the galaxy-halo connection. And then we have mock galaxy catalogs, which we can calculate all these summary statistics like galaxy clustering and galaxy-galaxy lensing, and then basically perform an apples-to-apples comparison to the actual observations, and thereby bypass the need, for example, for some analytic halo model. So yeah, all this is possible with several advancements also in software. So in our work, we make extensive use of this open source Python package called HaloTools, which was developed by one of the co-authors of this study. Another thing that was really required for this study is the development of large suites of cosmological simulations that probe different cosmological parameters. Because only with those it's possible to really ask what cosmological parameters, which simulations better fit the observations in the nonlinear regime. And so there are several examples, like for example, the CAMELS or the Quixote suite. In this work, we actually use the Aemulus simulation suite, which you can see here. Basically, this plot shows the cosmological parameters probed by this simulation suite. And finally, motivation for this work, for our group in particular, was an effect called lensing is low. So when you take a galaxy sample, like for example the Baryon sample we will analyze, and you model the clustering properties of these galaxies down to very nonlinear scales, and you assume cosmological parameters consistent with the Planck CMB parameters, you can actually make very precise predictions for what the expected galaxy-galaxy lensing amplitude should look like. So it's shown here, the results from our 2021 study. The different bands here are the predictions for the galaxy-galaxy lensing amplitude. But once you actually measure the lensing amplitude with data, you typically find that the measured lensing amplitude is lower than what you predict. And so that's the lensing is low effect. Now in this work from 2021, we used lensing measurements from LOWZ cross-correlated with the lensing catalog from SDSS, and we found very significant tensions with the Planck CMB predictions. And these lensing measurements were low both on high nonlinear scales but also on fairly large scales and for different galaxy samples, as you can see in these 3 different panels. And this was very surprising back then, that this tension was so strong even on large scales. And so it was important to us to see whether we can verify this with updated lensing measurements from the Dark Energy Survey and the kilodegree survey, which have vastly improved systematics. Yeah, so in this work, we're going to analyze galaxies from the Baryon Oscillation Spectroscopic Survey, particularly the LOWZ subset of the BOSS survey. This is a sample of luminous red galaxies at redshifts from around 0.1 to 0.5.
What I was wondering about when looking at things like this is, as you said, the lines here are predictions from using Planck cosmology, and then, okay, the dashes are the measurements. What is stopping one from taking the measured data and saying, here is the measured value of sigma S8, omega matter, etc.? And because I guess this is indicating that probably if one could do that, S8 would also be low, but what is stopping one from doing that?
Yes, so this is all based on predictions from a single simulation, right, that is consistent with Planck. In order to convert this into constraints on S8, you would need to marginalize this over cosmological parameters and have predictions for different cosmologies. The other reason why you shouldn't directly try to read off cosmological constraints from that is that this also includes high nonlinear scales, for which you would have to marginalize over the impact of baryons and also other astrophysical effects like galaxy assembly bias, which for this study we actually didn't do. So that's why you have to be a bit cautious about directly inferring cosmology from these plots.
Okay, so I can't be a crazy theorist and say what ratio of sigma 8 would I need to drop everything by a proportional.
You can estimate it roughly. It would be roughly like the ratio between the prediction to the observation to the prediction, like the power of 2/3. That's how much you need to lower.
Okay. Well, that's a homework for the viewer. Yeah, let's get into the details in what did you do in the paper? What is galaxy-galaxy lensing, and how did you use redshift-space distortions to get these constraints?
All right, yes. So let me first introduce the observations that we're going to use in this work. So as I said, we're going to analyze the LOWZ subset of the BOSS galaxy sample, a sample of luminous red galaxies. And one observation we're going to use is the redshift-space clustering of these galaxies. So we're measuring basically the amount of pairs separated by some line of sight direction, r pi, and some perpendicular direction, rp. And this two-point correlation function in redshift space typically looks something like you can see there. On very small scales, you have the very prominent finger of God effect that is caused by galaxies orbiting inside the dark matter halos of their hosts. And on large scales, you can see the Kaiser effect. I just overlay here a circle so you can see that along the line of sight, the distribution is squashed. And that's because of the infalling motions of galaxies towards overdensities. And so this Kaiser effect is what we will use to constrain cosmic structure growth and get constraints on S8. And I also would like to show this plot here because it's coming from actual data, and it shows you that even on those small scales, so below 30 megaparsec, what we're going to analyze here, there is abundant cosmological information that we can potentially extract. In addition to galaxy redshift space clustering, we're also going to use measurements of galaxy lensing. So here we use this gravitational lensing effect, whereby the shapes of some background galaxies will be distorted by some foreground mass distribution. In this case, we will trace the foreground mass distribution with LOWZXLOWZ galaxies, and the shapes of these background galaxies will come from lensing catalogs from the Dark Energy Survey Year 3 dataset, as well as the Kilodegree Survey 1000 square degree dataset. By analyzing these distortions of the background galaxies, we get a measure of the so-called excess surface density around the LOWZ galaxies. You can see the definition of the excess surface density here. It's defined as the mean surface mass density inside a circle centered on the LOWZ galaxy minus the surface mass density at the boundary. In other words, it's a measure of the enclosed mass within a certain radius around the LOWZ galaxy. So I want to advertise that all these measurements for this paper have been performed with publicly available data using this dsigma Python package. So this is a general purpose lensing package that everyone can use to measure galaxy-galaxy lensing for arbitrary lensing datasets, including DS, KiDS, but also, for example, the hypersuprime cam data or the CFHT lens data. So if you want to reproduce lensing measurements in our paper or for other lenses, that can easily be done.
Is there a reason why, I guess, is CFHT lens now a little bit out of date? But maybe not. But and is there a reason why you didn't use them and hypersupreme cam in your own analysis?
Yes, that's a really good question. So CFHT lens is a slightly old data set, similar to SDSS. It's not as good when it comes to controlling for systematics. HSC is a very powerful data set. The problem with HSC compared to KiDS and DS is that it covers a smaller sky area, which means that the galaxy-galaxy lensing measurements do not have a very high signal-to-noise on the scales that we analyze. They are very powerful on these very small scales, like 2.5 megaparsec and smaller. Also, HSC has larger systematic uncertainties than DS and KiDS. For HSC, the systematic uncertainty is around 5%, whereas for DS and KiDS of the order of 2%. All right, so here I just compare the galaxy-galaxy lensing measurements that we used in our work against older lensing measurements coming from cross-correlating LOWZ galaxies with shape catalogs from SDSS. We analyzed 3 different samples of LOWZ galaxies in redshift range from 0.18 to 0.43. What you can see here is that in terms of statistical constraining power, the SS measurements are actually still very competitive. You can see they actually have the highest signal-to-noise, especially on large scales. But as I said, DS and KiDS have vastly improved systematic calibrations, because of which we have much more trust in the lensing measurements of DS and KiDS. Additionally, we actually seem to find some hint that the DS measurements are slightly higher than those from SDSS, which partially explains the somewhat strong lensing is low effects and also S8 results that we have obtained or have been obtained in previous works.
Why is it that, on the large scales, I guess, maybe SDSS is doing better just because it sees more of the sky. Why is it still doing better on small scales?
Yes, that's a good question. So SDSS has the advantage here that A, it's a very large sky area, much larger than DS and KiDS, and also, basically by definition, it has perfect sky overlap with LOWZ. So if we want to cross-correlate LOWZ with SSS.
I see. So even though DS and KiDS have viewed a reasonable chunk of the sky, it's not, it's not the same part of the sky as LOWZ everywhere.
Exactly. So DS is primarily in the south and BOSS is primarily in the north. If LOWZ and DS would overlap perfectly, those would have like factor of 2 better signal noise.
I see. So which experiment do we need to wait for that will be the equivalent of having that?
For that, ideally, would have a spectroscopic survey in the south. The problem we have is basically that DES and also LSST are observing the south, whereas like DESI, follow-up of BOSS, is still in the north. So it will kind of like, if they were in the same hemisphere, that would really make things better for these kinds of analysis. So as I said, we're also going to use the combination of galaxy clustering and galaxy-galaxy lensing to constrain S8. As I mentioned before, Redshift-Space clustering by itself, without lensing, already constrains S8. But we can remove this sensitivity by looking at the projected clustering. Basically what we're doing is we're going to integrate the two-point correlation function Redshift-Space along line of sight direction and thereby remove the dependency on Redshift-Space distortions. We're basically going to measure something called WP. This measurement of galaxy clustering on large scales is basically sensitive to the linear bias squared and sigma 8 squared. If you combine this with galaxy-galaxy lensing, delta sigma, which is sensitive to the bias as well as omega matter and sigma 8 squared, the combination of these two measurements you can use to constrain omega matter and sigma 8. So this shows you that you can get a constraint on S8. Of course, it's only a simplistic picture that works on large scales, but I hope you get the idea that the combination of these two measurements can be used to constrain S8 in a way that is insensitive to Redshift-Space distortions.
And if one wanted to unpack these kind of dependencies, the reason the Redshift-Space distortion-y things depend on bias times sigma 8 is...
Because it's an autocorrelation function, right? So you...
Right, yeah, okay. And then the galaxy lensing only depends on one factor of B because it's also... The lensing is not being done by anything to do with a bias, whereas the...
it's only the matter, yeah.
Yeah, and then the reason why the Redshift-Space distortions doesn't depend on omega matter is...
Because really just measuring the matter-matter correlation function, the galaxy correlation function, right? So, right, the galaxy-galaxy lensing is you're sensitive to the galaxy matter correlation function, but if you just increase the amount of matter by a factor of 2, all the shape distortions will also increase by a factor of 2. So these are the measurements that we're going to use, and we're going to compare them against simulated mock galaxy catalogs to ultimately obtain cosmological constraints. So in this work, we first, of course, need cosmological simulations. And so here we're going to use the Aemulus simulation suite. This is a suite of 40 different n-body simulations, dark matter only, of cosmic structure formation. They trace around 1,400 cubed particles in a 1 gigaparsec cubed volume. They have different cosmological parameters, which are shown here. So in this corner plot, each point corresponds to one simulation of the Aemulus simulation suite. They trace roughly the 4 sigma contours of a combined analysis of CMB, BAO plus supernova, where the CMB constraints come either from WMAP9 or from the Planck analysis. And so the resolution of these simulations is fairly good and good enough to analyze the clustering and lensing of luminous red galaxies in the BOSS-LOWZ sample.
What's the difference between the red dots and the black dots?
That's a small detail. Those are the so-called test simulations of the Aemulus simulation suite. So these are just simulations that were used to verify that certain properties are converged, that the emulators that the Aemulus simulation, the Aemulus group designed were accurate. That's what those small dots are. They're not part of these 40 simulations that I initially referred to. And so what we now need is a recipe to relate the dark matter simulations and the corresponding halo catalogs to mock galaxy catalogs. And so the way we're going to do this is the backbone of our galaxy connection model is a halo occupation distribution model, HOD. So you parameterize what is the average number of galaxies as a function of halo mass. And you separate between central galaxies that live in the centers of dark matter halos and satellite galaxies that orbit in the outskirts. And I try to visualize here the different parameters in this parameterization. So for centrals, we assume that they basically follow an error function that has a plateau that Doesn't need to be 1, but somewhere between, 0 and 1. And similarly, for satellites, there's a possibility to have more than one satellite per dark matter halo, and so therefore this is modeled with a power law with a low mass cutoff. Now this HOD model describes what is the average number of galaxies as a function of halo mass only. By itself, this would not allow for the possibility of what's known as galaxy assembly bias, namely that the number of galaxies may depend on other halo properties besides mass, like for example halo age or halo concentration. So we also allow for galaxy assembly bias by further perturbing this average number of galaxies per halo based on its concentration. Basically, for each halo, we ask, has this halo a concentration that is above or below the average concentration in that halo mass range, and then we'll assign it a number of galaxies that is either above or below the average, and the spread between low and high mass, the spread between the low and high concentration halos are two additional free parameters, ASEN and ASET, in this parameterization. And so thereby we also marginalize over galaxy assembly bias. And finally, since we're also modeling the distribution of galaxies down to very nonlinear scales, down to the one halo regime, the scales of individual dark matter halos, we also have to worry about what is the distribution, the phase-based distribution of galaxies inside those halos. For example, satellites are broadly expected to trace the distribution of matter within the dark matter halo, but they might still be spatially biased in the sense that they might be more centrally concentrated or might be more in the outskirts in dark matter halo compared to the dark matter distribution. And so all this is modeled with this parameter eta, describing the radial distribution of satellites. And finally, we also model in detail the velocity distribution of centroids and satellites. So for satellites, you can very accurately predict the velocity dispersion based on the Wheeler theorem, but there are various reasons why you expect there might be deviations from the Wheeler theorem expectation. And so with additional free scaling of the velocities of satellites, and similarly for central galaxies, you might assume that those are not sitting still at the centers of dark matter halos, but for whatever reason might be wiggling around the halo center. And so therefore, we also allow some additional velocity offset for centroids, something that turns out to be very important to get unbiased constraints from redshift-space distortions.
Actually, maybe a quick question at this point. So the mock catalogs have a bunch of parameters. Those parameters are they a part of your general fit in the end, but you say you've made the mock catalog, so I presume you've chosen some set of parameters to make the catalog.
You make those catalogs and you compare against observations, so you have a likelihood, and then do basic MCMC over these parameters.
Okay, so you've got 40 different simulations, but more than 40 different mock catalogs.
Yes, a very large number, yeah. So I described how we can construct mock galaxy catalogs for these 4 different simulations as a function of different galaxy connection parameters. But how do we actually go from these mock galaxy catalogs to actual cosmological parameter constraints? So there are different methods that have been proposed in literature, including, for example, emulation, whereby you build a library of different cosmological parameters and galaxy connection parameters and their respective clustering and lensing predictions. And then you feed this into a machine learning algorithm and try to generalize this for arbitrary cosmological parameters. In this work, we use a slightly simpler approach that was described in this 2019 paper. So we have these 4 different cosmological simulations with different cosmological parameters. For each of those simulations, we calculate a summary statistic that describes how well this simulation fits the observations after marginalizing over uncertainties in the galaxy connection parameters. The summary statistic can either be the marginal likelihood, marginalized over the galaxy connection parameters, or the profile likelihood, so the best fit likelihood, again after marginalizing over the galaxy connection parameters. And then you just have to generalize how this summary statistic, the likelihood, depends on the cosmological parameters of the underlying simulation. So here's how this would look in practice. So in this paper, we did some mock analysis of galaxy redshift-space clustering. We know from linear theory on large scales, galaxy redshift-space clustering should be sensitive to the cosmological parameter f sigma 8. So here we plot the likelihood of each simulation as a function of its f sigma 8 value. You can see a very strong dependence of the likelihood in f sigma 8, such that it peaks at a value of around 0.47, which coincidentally is the f sigma 8 value of the input mock catalog that we're analyzing here. Through all these points, you can see goes a smooth line. That's the black line. That is just a model for how the likelihood depends on f sigma 8. You can see there is some scatter around this line. Part of the reason is that these different simulations have a finite volume, which means that there is stochasticity in the prediction of galaxy clustering, and thereby also stochasticity regarding the overall likelihood of each simulation. Once you have fit this relation, you can basically read off your cosmological parameters. In this case, in the top panel, you can see the implied posterior constraint on f sigma 8. And so we're going to use a very similar approach in this work. In this case, the summary statistic will be the profile likelihood, so the maximum likelihood marginalized over all galaxy connection parameters, which also means that we're insensitive, for example, to prior volume effects regarding the priors on galaxy connection parameters, which to some extent are arbitrary. Before actually applying all this to the real data, we performed tests on detailed mock catalogs to ensure that our analysis pipeline yields unbiased results. And so in this case, we created mock galaxy catalogs by taking the unit simulations and applying subhalo abundance match to them. Subhalo abundance matching is an alternative way to relate dark matter halos to galaxy catalogs and an alternative way to create mock galaxy catalogs. The important point is that it's a different method, and thereby several of the assumptions that we put into the HOD modeling might be violated, and so we can see to what extent this may bias cosmological parameters, if at all. Fortunately, we find that there is no indication of a bias. So that's what you can see in this plot. So in each panel, the yellow line and star indicate the input values of the mock galaxy catalog. It's basically the Planck value. The gray bands show our implicit prior. The reason for that is that we have these Aemulus simulations, and they only probe a certain part of cosmological parameter space. And so we can't really constrain cosmological parameters outside of this parameter space. And so therefore we put an implicit prior, basically an ellipsoid centered on these different Aemulus parameters. So that's the gray line. And so then the main results here are the different cosmological parameter constraints. The purple line is the result we would obtain from a combination of projected clustering and galaxy-galaxy lensing. So in this case, we're getting S8 constraints from lensing. The blue line is coming from only galaxy redshift-space clustering. So here the constraints come from RSDs. And finally, the red line is if we combine both redshift-space clustering as well as galaxy-galaxy lensing. In all cases, we can see that we get unbiased constraints on this S8 parameter. On the other hand, omega matter is not very much constrained, at least within these Aemulus priors. You can see our posterior constraints are very close to the prior. We nominally get some constraints on the dark energy equation of state, but this is primarily caused because the prior indicates a correlation between W and S8. And so thereby constraining S8, we indirectly constrain W, but it's not that we directly constrain W, it's more through this degeneracy.
And is it okay that you have this narrow range of cosmology for the data because the data is more constraining than the prior? Because so you don't get this effect here?
Yes, yeah. Also, before applying this to the real data, we perform our analysis blindly. So we follow the blinding procedure that was introduced in the Dark Energy Survey Year 3 analysis. That means we perturb the actual galaxy-galaxy lensing measurements as well as galaxy redshift-space clustering measurements in such a way that the inferred value of S8 is shifted by a random amount, at the same time in a way that keeps the goodness of fit basically or close to unchanged. So we test that this blinding procedure works as expected on mock galaxy catalogs. It shifts the S8 posterior by a predefined amount, and it also keeps the goodness of fit basically unchanged or close to unchanged. And so all the analysis was first performed on the blinded data, on the blind data vector. And only after we were happy with the goodness of fit and all details of the analysis, and all the authors agreed on this, we unblinded data and actually saw our cosmological constraints. And so this is what data fits look like. As I mentioned earlier, we have 3 different samples of BOSS-LOWZ galaxies in different redshift slices. Additionally, the BOSS galaxies have slightly different photometric offsets in the northern and southern galactic cap, and therefore we analyze them separately in this work, which ultimately means that we have 3 times 2, so 6 different galaxy samples. The top half, you can see the galaxy redshift space clustering measurements. We decompose this 2-dimensional galaxy redshift space clustering measurements into multipoles. So in yellow, you can see the monopole, red is the quadrupole, and purple is the hexadecapole. The lower panel shows the galaxy lensing measurements. For the northern galactic cap, those measurements basically only come from the kilodegree survey, and for the southern galactic cap, those come from the dark energy survey.
And A, B, and C are increasing in redshift or decreasing in redshift?
Increasing. Each of those panels, the gray bands indicate the range of scales that we do not consider for our cosmological analysis. Most importantly, for the galaxy lensing measurements, we do not model scales smaller than 2.5 megaparsec. The reason for that is that in this analysis, we do not model the impact of baryons on the matter distribution. And so thereby, we only include those scales that be unaffected by baryonic feedback in order to be conservative.
And baryonic feedback is less relevant to the top data?
Right. So for galaxy clustering, we do have recipes for how to model, or there's freedom in how to model the phase space distribution of galaxies within dark matter halos. So you already have some freedom to move galaxies within dark matter halos around. So therefore, this will be the general with baryonic feedback, but we don't have an explicit model for how the matter within dark matter halos is shifted around by baryons. So therefore, this would only affect galaxy lensing, and is implicitly modeled over with in galaxy redshift space clustering. You can see the measurements here with arrow bars, and the solid lines are our best fit model predictions. We got a very good fit to all the available data. We have around 180 data points, and the reduced chi-square is of order 1.
Okay, and just kind of stupid question, the best fit is to all of the top panel at once and to all of the bottom panel at once, separately though, and not to each line at once.
There's a consistent cosmology that made the predictions for all these 12 different panels.
All 12. Okay, I thought it was 6 and 6. Yeah, okay, all 12. Cool.
All right, and so the main result of this paper are, of course, our constraints on S8. So one thing that we show is that by including high nonlinear scales, we get substantially improved cosmological parameter constraints, particularly on S8. The main S8 constraints I want to highlight here. So in green, by the star, you can see the constraints coming from the combination of projected clustering and galaxy-galaxy lensing. And the red star are the constraints that come only from galaxy redshift space clustering. And so again, these are two complementary, largely independent ways to constrain S8, and they're very consistent with each other. We can also combine them, which is shown by the gray star. This is if we analyze both galaxy redshift space clustering as well as galaxy-galaxy lensing. Most importantly, these different constraints are very consistent with other large-scale structure probes, and they're also around 2 sigma below the Planck CMB value. So by while they're not in of itself proof in S8 tension, they provide additional evidence for the possibility of such a tension with an analysis that is statistically fairly independent to large-scale only studies.
Your significance is actually, like, degree of anomalousness has increased relative to the same analysis methods. I guess it's less significant maybe than the cosmic shear, but more significant than other say redshift space clustering stuff.
Yeah, so something that's very worth highlighting are our S8 constraints that come from redshift space clustering. So you can see there are 3 different constraints coming from redshift space clustering. The first 2, by Ivanov and Philcox, they're based on the analysis of both BOSS-LOWZ and BOSS-CMASS. That's almost a 3 times larger galaxy sample, but it's only focused on large scales. Here we're only analyzing a smaller subset on the low-Z sample, but by including high nonlinear scales, we actually get a more stringent constraint on S8 that's also now very consistent with constraints coming from cosmic shear and galaxy-galaxy lensing.
I have what feels like a maybe slightly dumb question, but combining the 2 things, I guess some of the data is overlapping, but I presume that was relatively straightforward in your pipeline to marginalize over the fact that it's the same.
You have the galaxy redshift space clustering measurements. We take into account covariance between different radial bins, right? And then you have these additional galaxy-galaxy lensing measurements. They're only measured on a very small sky area, and so thereby there's almost no correlation in the data, right? Because they're measured over like thousands of square degrees. The overlap is only a few hundred square degrees.
Awesome. So yeah, where do we go to next with this? I guess one direction is just waiting for more data to apply the same methods to, but can we push to even more nonlinear scales and what else is coming in the future?
Yes, so this is a very good segue into what we're going to work on next. So as you just said, and as I mentioned a few minutes ago, for the galaxy-galaxy lensing measurements, we're actually not using scales below 2.5 megaparsec. Again, the reason is that those scales would be strongly affected by the impact of baryons and uncertainties on baryonic physics. So we wanted to be conservative. But we're really throwing away a large amount of data. So if you, for example, calculate the signal to noise of the full range of scales going down to 0.1 megaparsec, the signal to noise is roughly a factor of 2 higher than the range we currently analyze. So there's a lot of potential cosmological information. So the first thing you would need is a model for baryonic physics and how it impacts the galaxy-galaxy lensing prediction. Having this model is only a first step, because you could take this into account. The problem is that you only have galaxy-galaxy lensing that would constrain it, and so it would be fully degenerate with cosmological constraints. So you need to have a second observation that you can use to constrain the amount of baryonic feedback and thereby break the degeneracy between baryons and S8. And so recently there was an exciting analysis by the Atacama Cosmology Telescope, the ACT collaboration. And so they cross-correlated BOSS galaxies, both low-Z and CMASS, with CMB secondary anisotropy maps, particularly maps of the thermal and kinetic LOWZXLOWZ effect. And thereby they can map out where is the gas around these BOSS galaxies. And in turn, you can use this to constrain the strengths of baryonic feedback and how it impacts the galaxy-galaxy lensing prediction. So it was very nicely shown in this paper by Amadeo and collaborators, where they predict what is the impact of baryons on the lensing amplitude compared to dark matter-only simulations. And that's basically, in this panel here, difference between the solid and the solid red and the solid blue line. You can see again this impact is primarily on small scales below 2.5 megaparsec, but on those small scales it has an effect of like 10 to 15%, and so it is important to take this into account. And so what we're currently working on is a combined analysis of galaxy redshift space clustering, galaxy-galaxy lensing, as well as the thermal LOWZXLOWZ effect, to ultimately jointly constrain cosmology, galaxy connection, as well as baryonic feedback.
That sounds very, very ambitious, and I mean, there's a lot of ways that systematics can creep in. But I mean, I guess this is what modern cosmology has to be, right? Like we're we either ignore the data or we use the data, and if we want to use the data, we need to break these degeneracies with baryons one way or another. So yeah,
it's the logical next first step. Of course, we can wait for more data. So dark energy survey and kilodegree survey and ACT, these are like state of the art, but BOSS already kind of an old data set, and the successor to BOSS is just around the corner, the dark energy spectroscopic instrument, which will soon finish year one observations. And so with DESI, we're going to have a larger sky area and also probing a larger redshift range with a higher sampling density for galaxies. And so this type of analysis will also be performed in the future with DESI. And so just by having more data and more lens galaxies, we expect much better cosmological constraints there as well. And finally, something that I also want to stress is the need for more tests on mock catalogs. So in this work, we have performed more tests on mock catalogs, more non-trivial tests on mock catalogs, but more work is needed, particularly on mock galaxy catalogs that come, for example, from hydrodynamical simulations, and to really verify them, especially also considering the increased constraining power that we expect from DESI, or once we also take into account baryonic feedback. And that's another area I think that's very important, and really to verify that constraints from nonlinear skills continue being robust.
I'm going to ask you a question that I've asked of the H0 people, and they couldn't answer it, and it's kind of a completely unfair question to be asking. Let's pretend that the SA tension is systematics. What's your leading speculation as to what it might be? And the reason it's an unfair question is, of course, if you had an idea of what it would be, you'd have included that systematic already in your analysis. But okay, if you want to answer the question, answer the question.
Yes, sure. This is a very interesting question. I think that's also what motivates this work. By thinking about a different type of analysis, going down to small scales, you have to some extent other systematics that you worry about. I think what's really interesting with the SA tension is that you have all these different observations, like cosmic shear, clustering plus lensing, redshift-space clustering, cluster counts, peculiar velocities, and they all point towards the same S8 value. So it is easy for me to think of an individual systematic that might affect cosmic shear or might affect cluster counts, but you would have to come up with several systematics that all shifted by the same amount. So that's why it's a bit more difficult. I couldn't directly come up with something that would explain all of them at the same time.
Whereas a systematic that actually affected the model is then going to affect everything. And then it wouldn't be a systematic, it would be new physics.
That's why I think that part is actually more robust regarding the SA tension, that we have so many different observations that are independent, really truly independent, that point over the same direction.
Yeah, what work being done in cosmology at the moment do you think is particularly underappreciated by the rest of the community?
Well, I really want to use this to thank the different collaborations, Dark Energy Survey, the kilodegree survey, for all the work that goes into making these different data sets publicly available and to make them be usable by other researchers. So this work here combines state-of-the-art data sets, BOSS, DS, and KiDS, and wasn't started as part of, or wasn't performed within any of these collaborations. And so I don't think we can thank enough the different people for different collaborations for making the data publicly available and documenting everything so that other people can use it. And I think this paper really also showcases the amount of information that you can extract from these data sets.
Yeah, and I mean, it's great that they do that, because then people like yourself and your collaborators and co-authors can do these analyses and bring a fresh eye to it, right? Like if you had done this analysis and it had ended up bang on the blue band, it would be, I mean, it would be good for the community. It might be bad for the individual collaborations, because then perhaps we'd suspect you'd found their mistake, but it's great for the community. And the fact that, an independent group has kind of relooked at it, and I mean, okay, in producing the data, they've made a set of assumptions that you haven't been able to undo because you've just got their data, but you've made analysis decisions that I guess are different and come out to a similar thing. So this is how science has to progress, that a result like this needs to be put under scrutiny, and the new physics that survives is the one that gets scrutinized and survives. And I guess this is one more step of scrutiny that they've allowed to happen by giving you the data.
Right. We try to give back to some extent, for example, by developing this Sigma pipeline, which makes it very easy for people to then use these public available data sets and make their own galaxy-galaxy lensing measurements and use in their own science.
So D Sigma is your... you didn't make it clear that it was...
Oh, it's my... I would say this was also developed as part of DESI. So I'm part of DESI, and we're going to use this pipeline. We're going to do these kind of 3x2 point studies also within DESI. And so we want to use the DS, HSC, and KiDS data sets.
Okay, thanks everyone for watching. If you like this, please do click the bell to be notified of new videos and subscribe as well. And click like to help with YouTube algorithms. It'll help the channel and help yourself because YouTube will know to recommend other content like this to you. If you have any questions or suggestions, please leave a comment. Otherwise, maybe you want to check out 2 recent talks on similar topics. The most recent one being the one by Andrzej Dwornik and Constance Mahany on pushing, I think it was just kids to nonlinear scales. And before that, a talk by Alexandra Amon and Naomi Robertson, also on going to these more nonlinear scales with both kids and Des. And thank you, Johannes, for a great talk.